Bueno, voy a pasar a presentar el próximo orador. Desde la Universidad de Columbia en New York tenemos el honor de contar con el doctor Yingcheng Sun, que va a hablarnos sobre sus avances en medicina basada en evidencia. From Columbia University, New York, we're honored to count with the presence of Dr. Yingcheng Sun, who is going to present the advances in evidence-based medicine. Thank you, Dr. Sun, for joining us today. We'll be showing your video first, and then people will ask questions.
Okay, thank you. No problem.
Muy bien, para el resto vamos a mostrar el video subtitulado del Dr. Sun y luego pueden hacer preguntas. Las pueden ir dejando en el chat a medida que van pasando. No me está dejando compartir el video. Voy a correrlo compartiendo pantalla.
No estás compartiendo, Ale.
Ya lo sé, porque no me está permitiendo, así que vamos a ir al plan B. Y si me dan 2 segundos, lo voy a abrir. Y sound.
Hi, everyone. I'm Yingcheng Sun from Columbia University in the United States. I'm very happy to join JIS 2021 to share my research. The topic for my talk is towards improved information retrieval for evidence-based medicine. A little bit introduction to myself. I work in the Department of Biomedical Informatics at Columbia University. My research interests include information retrieval, machine learning, and software engineering with applications in clinical informatics. Here are my website and email address. Sorry, I cannot speak Spanish, but English and Chinese are both good to me. In this talk, I will first introduce the background and then present my work in improving the search of clinical trial, patient cohort, and medical evidence. So evidence-based medicine or evidence-based care is a model aims to use current best evidence in making decisions about the care of individual patients. It is important in healthcare to achieve improved quality and patient satisfaction and reduce cost. Here's a question: how is the high quality evidence created? We know that evidence can be categorized into different levels. For high quality evidence, first, we need a randomized controlled trial and hire enough patients to participate in the trial. And the study results will be published as clinical literature. The evidence is within the literature. Now we have a problem. In each of these 3 steps, the resource is usually too rich, and sometimes it's hard for us to find what we need efficiently. For example, we have almost 400,000 clinical studies registered in clinicaltrials.gov, and the number still grows fast. We have more and more electronic health records, the EHR data, and every year, hundreds of thousands of RCT literature with study results are published. Given such a huge data, can we exactly find the target information efficiently? For example, for patients who want to join clinical studies, can we quickly recommend eligible trials to them? Or they can find trials themselves based on their own conditions. For a trial investigator or researcher, they might care about this question. Will there be enough patients for this new trial? A clinician might be interested in the best medical evidence, such as how does the intervention work for this disease? So first, let's look at the clinical trial search. What does a clinical trial look like? This is a snippet of a clinical trial summary from clinicaltrials.gov. We can see it has study type, estimated enrollment, intervention model, and some other elements. They're all unstructured, free text. Given hundreds of thousands of trials like this, how can we find the trials we're interested in? Basically, there are two types of methods. One is keyword-based research, like clinicaltrials.gov, NIH Clinical Center. In their interfaces, you can use multiple keywords or conditions to search. The other is questionnaire-based search. After answering a couple of trial-related questions, you can find eligible trials. I'm thinking, can we improve the search methods? We noticed that the keyword-based search usually returns too many results. And if you want to narrow down the search to a more specific scope, you might need to input a lot of items, a lot of different keywords. Like this, it takes time and labor. Can we use a trial as a query? I'm thinking, suppose that I have already had a trial in my hand, and can I find other trials similar to it? In this case, you do not need to construct a complex query. Based on medical domain expert suggestions, certain common data elements from clinical trial summary were extracted and used as similarity features, such as study type, masking, phase, study period, location, condition name, or eligibility criteria. They can be categorized into 4 different types. For each type of feature, we have a specific metric. For categorical variables like masking phase, we measure the percentage of shared categories. For free text, like condition name, eligibility criteria, we use the word embedding to measure the semantic similarity. Eligible criteria are usually very long, so we extract the key elements to avoid overfitting. For temporal interval, we measure whether there is time overlap. For geographical, a decreasing function to give the short distance a high value and the long distance a short value, a low value. The trial similarity is a weighted average of all features. We developed an interface to assist in finding similar trials. Given an example, target trial. This shows architecture. Clinical trials are first exported from clinicaltrials.gov, and then features are extracted. Users are able to adjust the weights applied to each feature by 4 different types of similarity metrics. Similar trials will be recognized given an example trial, and the results will be visualized. Here's a short video. You can input a trial ID here and set the number of trials you want to return, and adjust the weights of each feature and to adjust the weight of each key elements of eligibility criteria. And then you will see the 10 most similar trials, their location, the heat map, and a lot of details of each trial. Next, I will discuss the dynamic questionnaire. A static questionnaire could be too long and will be inapplicable with inapplicable questions. So dynamic questionnaire is widely used now. It is a decision tree structure. After answering question, you will go to different branches based on your answer. And the list of eligible trials will be updated. It is very flexible for users to narrow down the search, but not flexible enough for the investigators because it still needs a lot of efforts to create those questions. And sometimes investigators do not create enough questions to filter trials. So we developed an automatic question generation pipeline for the dynamic questionnaire using natural language processing method. First, entities are recognized from eligible criteria and categorized, and then mapped to standard concepts. All these steps are based on a data model called UMAP data model, the common data model. You can also choose UML set data model. For each type of concept, we developed a question template. For example, if the concept is a condition, the question will be, have you ever been diagnosed with the cough or dyspnea? With this question generation pipeline, we developed a dynamic questionnaire for COVID-19 trials last year. COVID-19 trials are first exported from clinicaltrials.gov and then indexed in the database by identifying the key concepts. Domain experts help to verify the process and update the incorrect instructions. We then develop an interface for users to answer questions and filter results. Here is a short video. You can input zip code and set the distance of radius and search the eligible COVID-19 trials. You can answer some 5 basic questions like age or whether you are in hospital. And then you come to the dynamic questionnaire process. We can answer questions here and the list will be dynamically updated. You see you are still eligible for 32 trials and you can check the size of each trial and it will be visualized. Okay, next. Just the patient cohort discovery. The rich EHR data facilitate cohort discovery. Given a cohort definition, we can easily run a circle query to find the cohort in the EHR database. For example, for this cohort definition, you can write a query like select patients where condition equals to COVID-19 and age between 18 and 80. And then you will have the cohort discovery. But the problem is when the cohort definition is long and complex like this, how can we search a cohort efficiently? The first type of method is to embed both cohort definition and EHR data into vectors and compare their similarity. This type of method needs large label data to train a model for embedding and it lacks transparency when we do patient search. The second type of method is similar to what I discussed in dynamic questionnaire. We can transfer the cohort definition to a circle query with natural language processing and query template, and then use this generative query to search the EHR database and get the cohort. We developed a cohort discovery framework. First, from free text clinical trial eligibility criteria, we identify entities and their domains and mapped them into standard concepts for following UMAP common data model. And then generate a query with circle template. The whole process is similar to the automatic questionnaire question generation pipeline for dynamic questionnaire, but the different part is we do not generate questions, but circle queries. here to search cohort from the EHR database. We noticed that the limitations of automatic annotations and found some eligibility criteria can be simplified. So, for example, the identification of logic or temporal information, sometimes they are incorrect and require further improvement. Some trivial, non-critical, redundant, or irrelevant criteria, they need to be removed to reduce the failure of cohort discovery. So we developed an editable user interface for users to edit their search, the automatic generated results. For example, if the automatic generated concept is incorrect, you can edit them, modify them. For example, this is the AD here is incorrectly mapped to the concept adrenal adenoma. You can change it to Alzheimer's disease with this interface. With discover cohort, we develop a metric to measure the population representativeness for each trial, and evaluated our framework with COVID-19 and T2DM trials on Columbia University Medical Center EHR data. We found that 85.7% of COVID-19 trials and 30.1% of T2DM trials have relatively poor representativeness. After removing or losing the criteria with low representativeness, the representativeness of the whole clinical trial can be improved. Next, let's look at the medical evidence retrieval. Evidence are usually in unstructured text in clinical literature, and the keyword-based search usually returns too many results. So PICO framework is commonly used now to find more specific answers. The P stands for participant, or patient, or problem. I stands for intervention. C stands for comparison, and O is outcome. So PICO-based literature research is like you can assign population as, for example, COVID-19 as P, and intervention name like hydrochloroquine as intervention as I, and use this to formulate a query to search from the database. But PICO-based search, that results still unclear for users to locate the evidence. It usually returns a list of PICO elements like this, but not evidence. So you can see that there are multiple types of participants and multiple types of outcomes. We don't know which population, like each child of COVID-19 or exposure to COVID-19, which one has death and time to clinical improvement. We don't know their connections. We need to go to the original literature to read and find what is the evidence. So the second question is, can we ask clinical question instead of using PICO elements to search? Because sometimes it's hard for users to formulate PICO concepts. So we developed an interactive natural language search engine for PICO-based medical evidence curation. Randomized controlled trial articles are first exported from PubMed.gov, and then we do the consonants classification and PICO element identification, and then articles are indexed in the database. So for the PICO element recognition and evidence identification, we use a deep learning model called Bluebird, and this model is pre-trained on PubMed.gov, the articles, article abstracts, and it is fine-tuned by our annotated datasets. For the right part, when a user inputs a query, it will be parsed and expanded by UML's database to increase the recall of the search. And the search results will be viralized, will be filtered first and then viralized to the users. Here is a short video of our search engine. You can search a question here, like do chloroquine or hydrochloroquine improve outcomes of COVID-19 infection? In the result page, you can filter the results by facets. In the article abstract page, the pickle elements are highlighted, and evidence propositions are also highlighted. And we also provide a pickle-based search tool, search interface. You can search by pickle elements combinations with Boolean logic. Here, you can also filter the results by query elements. And okay, this is the demo. Now it's a conclusion. There's still many work to continue improving clinical trial information retrieval. Clinical information retrieval, yeah. Such as clinical trial recommendation, optimization, or evidence similarity search, similarity or evidence clustering. The various skills and methods can be applied to improving the clinical information retrieval, such as machine learning, data mining, or software engineering skills. So that's all my presentation. Thank you, everyone, and welcome to talk with me and discuss the research. Thank you.
Thank you very much. This was a great presentation, and it's truly amazing what you've developed so far. So I'm wondering, what sort of infrastructure did all that work need? How many servers do you have? It's a lot, it seems.
Hi, Alejandro. So you asking how many search?
No, I mean, what sort of machines do you have to run all those searches? It seems like a lot of computational effort to run all of those algorithms.
What kind of machine? We're using a server but right now we're using Google, a Google Cloud platform. We apply the credit from Google. They offer a 2-year free trial for us. We put all of our applications on that platform. So our applications can run fast and efficiently. So yeah, that's a good question. You do need a good server to host all those search engines. It takes some resource.
Great, thank you. And I was wondering, what's the scope of this? Will your system be available to certain, I don't know, universities or hospitals, or are you planning to let people in the world access those search engines?
Okay, yeah, so those search engines are free to everybody and all the world. You can see our clinical trial search engine, the COVID-19 trial founder. It was released last year, and we noticed that the visitors coming from all over the world, more than 1,000 visitors coming from United States, North America, South America, Asia. So most of the visitors are from United States, but all those applications are free to everybody. So if their addresses are in our lab's website. If you're interested, you can visit my personal page or my lab's page to check those addresses and try those applications.
Thank you. Traduzco brevemente. Lo que dijo el Dr. Sun es que usan Google Cloud Server, o sea, el servidor de Google, para realizar los algoritmos pesados. Esa fue una de las preguntas. Y la otra pregunta es si las herramientas de búsqueda están abiertas a todo el mundo. Y me respondió que sí, que sus URL están en la presentación. Después las presentaciones van a estar disponibles para el público. So I was translating. On the chat room, we have a comment saying, really impressive, Dr. Sun. Thank you for your presentation.
Thank you. Alejandro, thank you, everybody. Okay.
¿Hay más preguntas? Si no, pasamos al próximo orador. Well, it seems like there are no more questions for now. We're very pleased with your presence, and we have another thank you from the chat room. And now we'll go on to the next talk. So thanks once more.
Okay.
Muchas gracias.
Thank you. Bye-bye.